XIO2200A PCI Express to 1394A chip by Texas Instruments. Welcome to the training module on Texas Instruments XIO2200A PCI Express to 1394A chip. This training module will go over the basics of PCI Express, including an overview of PCI Express, differences between PCI and PCI Express, and the types of PCI Express devices. It will also introduce XIO2200A to 1394 base endpoint devices. Over the past few years, the industry has started the migration from PCI to PCI Express. However, many designers and engineers still ask, what exactly is PCI Express? As a starting point, PCI Express is a high-speed, low-voltage differential serial communication interconnect between two devices. This point-to-point communication mechanism was defined by an industry consortium known as the Peripheral Component Interconnect Special Interest Group, or PCI SIG. The first revision of the PCI Express base specification was in 2002, and multiple revisions have been made since then to make improvements. PCI Express can be broken down to two speed grades specified by PCI Express base specifications. Gen 1 at 2.5 gigabits per second, and Gen 2 at 5.0 gigabits per second. This training module will focus on Gen 1 speeds of 2.5 gigabits per second. PCI Express operates at a high-speed serial rate of 2.5 gigabits per second and utilizes low-voltage differential signaling to achieve this. Coming from PCI, this technology doubles the existing theoretical bandwidth of PCI while also utilizing a much lower pin count. This table illustrates some basic differences between PCI Express and traditional PCI. PCI Express utilizes a high-speed serial bus which uses low-voltage differential signaling to transmit data across the bus. This is a drastic change from the parallel bus PCI employed. PCI Express is also a point-to-point architecture, whilst PCI was a shared bus architecture. With the high bandwidth capability of PCI Express, isochronous data transfer is supported, and OOS is much improved over what PCI offered. A physical connection between two PCI Express devices is broken down into subparts, as can be seen on the figure. A lane consists of signal pairs in each direction, with each signal of the pair made up of two wires. These two wires are used to transmit the differential signals across the lane. The peak-to-peak signaling voltage of the transmitter ranges from 800 millivolts to 1200 millivolts, while the differential peak voltage is half of these values. Common mode voltage can be anywhere between 0 and 3.6 volts, making the transmission of the data fairly low power. A full PCI Express link is a collection of one or more symmetric lanes in each direction, and combinations are specified by PCI SIG in the base specification. A 1 times link consists of one lane or one differential single pair in each direction for a total of 4 signals. A 32 times link consists of 32 lanes or 32 signal pairs in each direction for a total of 128 signals. Lanes can be defined as times 1, times 2, times 4, times 8, times 12, times 16, or times 32. There are many attractive features that come built into the PCI Express specification. Besides having a point-to-point connection between two devices, utilizing a serial bus requires fewer pins in design versus that of PCI. With lane aggregation, PCI Express is very scalable to bandwidth-intensive applications. Since PCI Express evolved from the PCI and PCI-X, migration is much easier. The same memory, I/O, and configuration address space is used in PCI Express as was used in PCI. In addition, PCI Express has a higher quality of service with improved data integrity and error handling. PCI Express is RAS capable, and data integrity is available at both the link level and at the transmit or receive level. The basic PCI Express topology includes 4 major components, including the root complex, bridges, switches, and endpoints. The root complex is the device that connects the CPU and memory subsystems to the total PCI Express fabric and can support one or more PCI Express ports. The example in this has 3 ports. A bridge device creates a bridge between PCI Express and another standard, typically a PCI or PCIX hierarchy. A switch is used to expand the PCI Express fabric, utilizing virtually PCI to PCI bridges as seen in the figure. Endpoint devices are simply peripheral devices that are either requesters or completers of PCI Express transactions. TI offers 4 different types of PCI Express device families, including physical layer or PHY devices, bridges, switches, and endpoints. PCI Express PHY devices are necessary when FPGAs in a system design do not have the functionality integrated. Connecting a PHY device to an FPGA allows the FPGA to then be part of the PCI Express fabric, and in turn can take advantage of the higher speed and bandwidth capability of the architecture. PCI Express switch devices are used to extend the PCI Express fabric, allowing for more devices or endpoints to be connected. PCI Express switch devices are used to extend the PCI Express fabric, allowing for more devices or endpoints to be connected. Endpoints are necessary to add peripheral capabilities to a PCI Express fabric. There are many examples of peripherals including 1394 controllers, Ethernet, USB, and graphics devices that can take advantage of the high bandwidth capabilities of PCI Express. The Texas Instruments XIO2200A is a single-function PCI Express to PCI local bus translation bridge where the PCI bus interface is internally connected to a 1394A2000 open host controller, link layer controller with a 2-port 1394A PHY. The device is capable of transferring data between the PCI Express bus and the 1394 bus at 100, 200, and 400 megabits per second. The XIO2200A provides 2 1394 ports that have separate cable bias. The device also supports IEEE standards such as 1394A2000 power down features for battery-operated applications and arbitration enhancements. The PCI Express to PCI translation bridge is proven compatibility and interoperability with leading PCIe chipsets and 1394A devices. The software programmable and hardware autonomous power management features for low-power applications such as Express Card. An external 2-wire serial EEPROM interface is provided to load the global unique ID for the 1394 fabric. The XIO2200A is available in either 176 ball GGW or ZGW MicroStar BGA or a 175 ball ZHH MicroStar BGA package. This slide shows a simplified block diagram of the basic architecture of the PCI Express to PCI bridge with 1394A OHCI and 2-port PHY. The top of the diagram is the PCI Express interface, and the 1394A OHCI with 2-port PHY is located at the bottom of the diagram. This figure represents a typical implementation of the XIO2200A PCI Express to PCI translation bridge with 1394A OHCI and 2-port PHY. The solution provides robust PCI Express link to 1394A cable port protocol conversion in a single semiconductor package. The XIO2200A operates only with a PCI Express link as the primary interface and the 1394A cable ports as the secondary interface. The XIO2200A requires either a differential 100 MHz common clock reference or a single-ended 125 MHz clock reference. The double EEPROM can be used to set various configuration registers, but is not necessary if those registers are settable via system software or BIOS. Up to 8 general-purpose inputs and outputs exist for further system customization. The 1394 core requires a standard 24.576 MHz crystal oscillator as described in the 1394A specification. The XIO2200A has an ×1 PCI Express interface that is fully compliant to the PCI Express base specifications revision 1.0a. The XIO2200A TX and RX terminals attached to the upstream PCI Express device over a 2.5 gigabits per second high-speed differential transmit and receive PCI Express times 1 link. The device requires an external reference clock for the PCI Express interface. The device is designed to meet all stated specifications when the reference clock input is within all PCI Express operating parameters. This includes both standard clock oscillator sources or spread spectrum clock oscillator sources. The XIO2200A PCI Express reset terminal connects to the upstream PCI Express device's preset output. The bridge also supports a PCI Express sideband wake feature. The device has two 1394 cable ports that operate at 100, 200, and 400 megabits per second. These ports are compliant with the IEEE standard 1394A2000 Amendment 1. This slide describes implementation considerations for the XIO2200A secondary 1394 cable ports. The figure illustrates the connection of the XIO2200A to a 1394 cable connector. For any unused 1394 port, the TPB plus and TPB minus terminals can be tied together and then pulled to ground through a 1K ohm resistor. The TPA plus and TPA minus terminals of an unused port can be left unconnected. There are 8 general-purpose I/O terminals in the XIO2200A. All 8 GPIO terminals are 3.3 volts tolerant. 3 of the GPIO terminals are shared with other miscellaneous functions. The remaining 5 terminals are always general-purpose inputs or outputs. All 8 GPIO terminals are individually configurable as either inputs or outputs by writing the corresponding bit in the GPIO control register at offset B4H. The GPIO data register at offset B6H exists to either read the logic state of the GPIO input or to set the logic state of the GPIO output. The power-up default state for the GPIO control register is input mode. In summary, PCI Express is the latest in high-speed serial technology, allowing for flexible connection options whilst utilizing less pins than traditional PCI. With improvements in RAS and QoS, PCI Express will be used for years to come. PCI Express endpoints devices are necessary to add peripheral capabilities to a PCI Express fabric. There are many examples of peripherals including 1394 controllers, Ethernet, USB, and graphics devices that can take advantage of high bandwidth capabilities of PCI Express. The XIO2200A is 1394 based endpoint devices as a PCI Express to PCI local bus translation bridge to provide full PCI Express and 1394A functionality and performance.